On the 2nd of October, something extraordinarily swift blazed through the Martian heavens. Stefan Burns, an amateur astrophotographer, discovered it while examining NASA's unprocessed images from the Perseverance rover. He assembled a time-lapse sequence from 9 minutes of compressed data, and there it appeared, racing at 60 kilometers per second against the regular drift of stars. However, this is where the situation becomes peculiar. Additional users began examining the identical images, claiming they observed not just one object, but several. Multiple rapidly moving anomalies appeared in the October 3rd data, along with an unexplained green luminous burst that remains a mystery. NASA had arranged this observation intentionally. Several Mars-orbiting spacecraft were positioned to capture the closest photographs ever taken of an interstellar object. The higher-resolution camera with 30-kilometer resolution capability, the ESAS Mars Express, and the ExoMars Trace Gas Orbiter all aimed at 3 Atlas during its October 3rd approach. Then came silence, no official photographs, no data publication, nothing whatsoever. Meanwhile, Harvard's Avi Loeb has just released findings that are unsettling the entire astronomical community. This object, 3 Atlas, might have been responsible for the legendary 1977 WOW signal. The probability of this being mere coincidence stands at 0.6%, yet the WOW signal connection represents only the opening chapter, because 3 Atlas is violating every established principle we have regarding comet behavior. It's generating industrial-quality nickel alloys in the vacuum of space. Its tail extends in the incorrect direction. It displays a green coloration when it shouldn't possess one, and it's traveling along a trajectory so precisely aligned with our world that the mathematical odds are astronomical. Some experts are designating it as the largest interstellar object ever identified. Others are calling it impossible. Avi Loeb is characterizing it as potentially artificial, and presently it's positioned behind the sun where observation is impossible, concealed, approaching its nearest point to our star. What will occur when it reemerges? Before we explore deeper, if you're finding this captivating, press that like button and subscribe so you won't miss what's approaching next. And share in the comments where you're watching from, what time it is in your location, and whether you believe we're observing one object or multiple. And if you wish to help this community expand, distribute this on X, Facebook, Reddit, or your messaging app. Thank you for consistently supporting us. Let's return to October 2nd. Stefan Burns wasn't searching for anything remarkable. He was merely processing the unfiltered image data that NASA makes publicly accessible from the Perseverance rover. The rover had received instructions to observe the night sky during a designated window when 3 Atlas was predicted to pass nearest to Mars, nearest being a comparative term we're discussing 29 million kilometers of separation. Burns compiled 9 minutes of sequential images and combined them into an animation. In astrophotography, this method reveals movement that would be imperceptible in a single frame. Stars appear to traverse the frame due to Mars' rotation. But this was distinct. Something was cutting across that movement at an angle that made no sense for a background star. The velocity was the initial indication. At 60 kilometers per second, 3 Atlas travels faster than nearly everything in our solar system. For reference, Earth circles the Sun at approximately 30 kilometers per second. The Parker Solar Probe, humanity's swiftest spacecraft, achieves 192 kilometers per second only at its closest solar approach. But 3 Atlas sustains this blistering velocity throughout its expedition. Burns published his animation online. Within hours, other amateur astronomers commenced their own analysis. And that's when someone named Nachtef, a German username translating to night monkey, made a statement that created ripples through the observing community. In the photographs from October 3rd, Nachtef documented, "You can even observe multiple comets, not one object, multiple." Another user, Alexander Plum, identified something else. What represents the flash at second 0003 marked with green? Return and watch Burns's animation frame by frame. There, at the 3-second mark, a brief green luminosity manifests. It's not a camera malfunction. It's not a cosmic ray strike which would manifest as a single brilliant pixel. This is a dispersed radiance, localized yet distinct. Green illumination in space has specific origins. On Earth, we associate it with auroras, with burning copper, with certain bioluminescent organisms. In space, green emission typically originates from oxygen, or from a molecule designated dicarbon, 2 carbon atoms bonded together. Comets occasionally radiate green when solar radiation excites dicarbon in their comas. But here's the complication. Spectroscopic analysis of 3 Atlas from the Very Large Telescope revealed virtually no dicarbon. The object is what astronomers characterize as chain-depleted. It shouldn't be radiating green. Yet photographs from ground-based telescopes in early September clearly displayed a green tint developing around the object. The green flash in the Mars images, if authentic, introduces another dimension to this enigma now. Regarding those multiple objects, this is where matters become speculative. But the speculation originates from people with telescopes and image processing software, not from people fabricating things. When you stabilize the star field in Burns's animation, when you compensate for Mars's rotation and the motion of the primary object, there appear to be at least 1 or 2 additional points of light traveling at different velocities. Could these be imaging artifacts? Absolutely. Could they be background asteroids that coincidentally appear in the frame? Possibly. Could they be separate fragments or even smaller objects accompanying 3 Atlas? That's the question nobody can answer yet. Reconnaissance Orbiter's HiRIS camera observed 3 Atlas on October 2nd between 1 and 4 in the morning Mars local time. The ESA's Trace Gas Orbiter and Mars Express both captured observations on October 3rd. These weren't casual photographs. These were coordinated, pre-planned scientific observations designed to gather the highest resolution data ever obtained of an interstellar object. HiRAS, the High Resolution Imaging Science Experiment, can distinguish features as small as 30 centimeters on Mars's surface from orbit. When directed at an object 29 million kilometers distant, it should still achieve a resolution of approximately 30 kilometers per pixel. That means if 3 Atlas has a nucleus 5 kilometers across, as recent estimates suggest, it should appear as a bright cluster of pixels in the HiRIC images. More significantly, HiRIC would be capable of distinguishing between a single compact nucleus and a fragmented or multi-component object. If there are multiple pieces, if there's a companion object, if there's anything unusual about the structure, high RIE would detect it. So where are the images? NASA's official statement has been minimal. The Mars orbiters successfully conducted their observations. Data is being processed. Updates will be provided as analysis continues. That was over 24 hours ago. In the world of space imaging, 24 hours is sufficient time to at least preview raw data. Some observers have noted that the United States government has been dealing with various administrative issues that have affected the release of scientific data. But ESA operates independently. They should have no such constraints. Yet ESA's images haven't appeared either. The silence feels intentional. And when official channels fall quiet, amateur observers start conversing. Because here's what we know with certainty: the Perseverance rover did capture something. Multiple amateur analysts examining the same publicly available raw data are detecting anomalies. The object or objects moved at velocities consistent with 3 Atlas, and there's that green flash that no one can explain. What we don't know is whether those apparent multiple objects are genuine, whether they're separate from the main comet, and what NASA and ESA observed with their far more powerful instruments. The October 3rd flyby represented the closest any spacecraft has ever approached an active interstellar object. This was our opportunity to understand what 3 Atlas really is, to observe its structure up close, to determine if it's behaving like a normal comet or like something else entirely. And as we await answers, the object itself continues its journey. Right now, it's approaching the Sun, moving deeper into the inner solar system, where Earth-based telescopes lose sight of it against the solar glare. By late October, it will pass behind the Sun from our perspective, completely hidden. And when it emerges in November or December, it will either confirm every natural explanation, or it will have done something that comets simply don't do. But before it vanishes, we need to discuss what the Mars observations were really searching for, and why the timing of this silence matters more than you might imagine. There's a pattern in how space agencies handle sensitive observations. When something routine is captured, the data appears within hours. Raw images populate public databases. Press releases get drafted. Scientists tweet their findings. When something unexpected appears, the silence extends. The technical explanation for the delay centers on data processing pipelines and calibration requirements. Mars orbiters don't transmit images in real time. They store observations on board, then beam them to Earth during scheduled communication windows. From there, the data moves through various processing stages: geometric correction, radiometric calibration, noise filtering. For a typical surface observation, this takes 6 to 12 hours. For a moving target against the starfield, perhaps twice that. We're now well past 48 hours since the October 3rd observations. But there's another factor at play. One that doesn't get mentioned in official statements, but filters through the community of researchers who depend on NASA data for their work. Budget constraints and administrative disruptions have created bottlenecks in data release protocols. Not a formal shutdown, but the kind of bureaucratic friction that transforms routine processes into delayed ones. Staff working reduced hours, priority systems getting reshuffled, review chains lengthening. ESA operates under different administrative structures. Yet there, Mars Express and ExoMars Trace Gas Orbiter images haven't appeared either. This suggests either a coordinated decision to withhold preliminary data until full analysis is complete, or technical challenges that both agencies are working through simultaneously. The question becomes, what would be challenging enough to cause this delay? Consider what these instruments were designed to observe. The Color and Stereo Surface Imaging System, CASIS, on the Trace Gas Orbiter can resolve features down to approximately 4.5 meters per pixel when imaging Mars, pointed at an object 29 million kilometers away. That resolution drops significantly, but the instrument's sensitivity remains high. It's designed to detect subtle color variations in Martian surface materials. If 3 Atlas was shedding multiple types of ice, if its coma showed compositional variations, if there were structurally distinct regions, CASIS would capture that. Mars Express carries the high-resolution stereo camera, which, despite its name, focuses on three-dimensional topography. For a distant comet, its stereo capability matters less than its ability to image across multiple wavelengths simultaneously. The camera can distinguish between dust, water, ice, carbon dioxide ice, and various minerals based on how they reflect different colors of light. Then there's the Mars Reconnaissance Orbiters, HIARC, which we've mentioned, but here's what we haven't discussed. HIRIE doesn't just take pictures. It collects data across 3 color bands, blue-green, red, and near-infrared. When pointed at a comet, those bands reveal different aspects of composition and activity. Blue-green light interacts with gases in the coma. Red and near-infrared penetrate through thin dust, revealing structure beneath. If the comet was releasing jets of material from specific locations on its nucleus, if those jets had different compositions, if the brightness varied across the object in ways that suggested a non-uniform surface, HIRSE would document all of it. And here's the thing about sensitive images. They sometimes show features that require consultation before release, not because of conspiracy, but because preliminary observations can be misinterpreted without proper context. If HIRIS captured something that looked unusual, mission scientists would want to rule out instrumental artifacts, cosmic ray hits, or processing errors before making the data public. But while we wait for official channels to open, there's Simeon Schmaus. Schmaus is an astrophotographer who specializes in processing raw planetary data. He's known in the community for his ability to extract signal from noisy images, to stabilize shaky video, to bring out subtle features that initial processing misses. On October 1st, a day before Stefan Burns's October 2nd time-lapse, Perseverance captured a series of night sky images. These were posted to NASA's raw image database, as all Perseverance images are. Within hours of being received on Earth, Schmaus downloaded them, applied his processing techniques, and claimed to see an early glimpse of 3 Atlas in those frames. The claim hasn't been independently verified. The object would have been extremely faint at that distance and angle, but if legitimate, it suggests the comet was detectable even before the main observation window. More intriguingly, Schmaus noted that the motion he detected didn't perfectly match the predicted trajectory. Close, but with a slight deviation. He posted his findings on social media, stating that more analysis was needed. but the preliminary results were intriguing. Then, like the official sources, he went quiet. Whether he's still analyzing, whether he found something he wants to confirm before discussing publicly, or whether he's been asked to hold off, we don't know. What we do know is that there's a gap between what should be routine disclosure and what's actually happening. A gap between the scheduled observations and the data we can examine. A gap that's filled with amateur discoveries, unexplained green flashes, and claims of multiple objects that nobody can officially confirm or deny. The Perseverance rover continues its surface mission. Its cameras remain functional. Its data continues uploading to the public database. But the specific images from those crucial nights, the ones that matter most, are the ones being scrutinized in silence. By October 3, Atlas will reach perihelion, its closest approach to the Sun. At that point, it will be entirely behind our star from Earth's perspective, invisible to ground-based telescopes and space-based observatories alike. The window for observation is closing. Whatever NASA and ESA observed, whatever Schmaus discovered, whatever is happening behind the review processes and data pipelines, the clock is running. Because if there's something unusual about this object, if those multiple points of light are real, if the green flash means something, we need to know before it disappears into solar glare. And if we don't get those answers, we'll have to wait until November when the comet emerges on the other side, potentially changed by its close encounter with the Sun, potentially having done something that natural comets don't do. But there's another reason the timing matters. Because while we've been focused on what the Mars observations might show, Avi Loeb has been looking backward, tracing 3 Atlas's path not just through our solar system, but through time. And what he found connects this object to one of the most famous unexplained signals in the history of astronomy. August 15, 1977, Ohio State University's Big Ear Radio Telescope was conducting a routine survey of the sky, searching for signals that might indicate technological civilizations beyond Earth. The telescope operated automatically, scanning narrow bands of radio frequencies, printing out intensity readings on continuous paper. Astronomer Jerry Emin was reviewing the printouts 3 days later when he noticed something that made him grab a red pen. A signal had appeared strong and narrowband, lasting exactly 72 seconds. The intensity was so far above background noise that Emin circled the alphanumeric sequence and wrote one word in the margin. Wow. The signal came from the direction of Sagittarius. Near the globular cluster M55, it was detected at a frequency of 1420 MHz, which sits within the protected radio astronomy band. No human transmissions are allowed at that frequency. The signal's bandwidth was narrow, less than 10 kHz, exactly what you'd expect from an artificial transmitter rather than a natural astronomical source. The Big Ear never detected it again. Follow-up observations found nothing. For nearly 50 years, the WOW signal has remained one of astronomy's deepest mysteries until Avi Loeb decided to calculate where 3 Atlas was on that date, working backward from the object's current trajectory and velocity. Loeb traced its path through space. In August 1977, 3 Atlas would have been approximately 600 astronomical units from Earth. That's 600 times the distance between Earth and the Sun. far out in the outer reaches of the solar system, but not yet in true interstellar space. The WOW signal originated from sky coordinates of right. Ascension 19 hours 25 minutes, declination minus 27 degrees. These coordinates point toward. Loeb calculated 3 Atlas's position on August 15, 1977. The object would have been at right ascension 19 hours 21 minutes, declination minus 19 degrees. 4 degrees separated in right ascension, 8 degrees in declination. In astronomical terms, that's remarkably close. The chance of 2 random directions in the sky aligning to within 9 degrees of each other, about 0.6%. But alignment alone doesn't prove causation. Loeb went further. If 3 Atlas transmitted the WOW signal, how powerful would the transmitter need to be? The signal intensity detected by Big Ear ranged from 54 to 212 Janskys. A Jansky is a unit measuring radio flux density. For comparison, the strongest radio sources in the sky, like the Sun or Jupiter, typically measure in the hundreds to thousands of Janskys when observed at specific frequencies. At a distance of 600 astronomical units, generating the received intensity would require a transmitter outputting between 0.5 gigawatt and 2 gigawatts of power. That's the output range of a typical nuclear power reactor on Earth. Not impossible. Not even particularly advanced by the standards of a civilization capable of interstellar travel, but notable because it's precisely the kind of power budget that would make sense for a deep space probe trying to communicate across vast distances. There's another detail. The WOW signal showed a slight frequency shift. It was detected at 1420.4556 MHz, which is about 10 kHz higher than the neutral hydrogen line frequency. This represents a blue shift, meaning the source was moving toward Earth. 3 Atlas is moving toward the Sun at approximately 60 kilometers per second. When you account for Earth's motion and geometry in August 1977, the relative velocity would produce a blue. Loeb calculated the expected shift. It's close to what was observed, though not a perfect match. The difference could be explained by uncertainties in the exact position and velocity vectors, or by the signal having been transmitted in a specific direction rather than omnidirectionally. Here's where it gets interesting from a strategic standpoint. If you're an intelligence wanting to announce your presence, broadcasting near the hydrogen line makes sense. Hydrogen is the most abundant element in the universe. The 21-centimeter hydrogen line is so fundamental to radio astronomy that any civilization capable of radio technology would monitor it. It's the galactic calling card frequency. The WOW signal lasted 72 seconds because of how the Big Ear telescope operated. It used to feed horns separated in the sky that listened to adjacent regions as Earth's rotation swept them across the target. Each feed horn had a window of 36 seconds. The signal appeared in both horns sequentially, creating the 70-second detection. This means the source was transmitting continuously, or at least for the duration that Big Ear could observe it. Not a brief pulse, but a sustained broadcast. If 3 Atlas was responsible, this raises immediate questions. Was it a beacon announcing presence to anyone listening? Was it a navigation pulse marking position for some other spacecraft? Was it an attempt at communication, encoding information we lacked the sophistication to decode? Or was it entirely unrelated, cosmic coincidence, where an interstellar comet happened to be aligned with a natural radio source we haven't yet identified? The problem is, we don't have radio telescope data on 3 Atlas. Not from August 1977, obviously, but not from now either. No observatory has reported pointing radio dishes at this object. The focus has been on optical observations, on spectroscopy, on imaging. The questions being asked are about composition and structure, not about whether it's transmitting. Loeb is arguing that needs to change immediately. The object is approaching perihelion. It's getting closer to the sun, which means higher temperatures, more activity, more energy available if there's any kind of technological system involved. If it transmitted once at 600 astronomical units, if it's designed to communicate at specific points in its journey, this would be the time. Radio telescopes, like the Very Large Array in New Mexico, the Arecibo successor facilities, even the vast arrays in China and Australia, could monitor 3 Atlas across multiple frequencies, not just the hydrogen line, but across the spectrum where artificial signals might appear. The observation would be straightforward. Point, listen, compare to background. Look for any narrow-band signals, any modulation patterns, any repetitive structures that natural sources don't produce. If there's nothing, FINIT costs a few hours of telescope time to rule out the hypothesis. But if there's something, if 3 Atlas is emitting radio signals, even faint ones, even intermittent ones, that changes everything about how we interpret this object. Because a comet doesn't broadcast. A chunk of ice and rock, even from another star system, doesn't generate radio signals at specific frequencies. Natural astronomical sources produce radio emissions, but they're broadband, chaotic, lacking the structure that indicates intention. The WOW signal had structure. It had a narrow bandwidth. It appeared at a meaningful frequency. And if Avi Loeb is right about the alignment, if the 0.6% coincidence is actually causation, then somewhere in the outer solar system 48 years ago, something transmitted a signal powerful enough for us to notice that something is now racing past Mars, hidden behind the sun from our perspective, doing things that comets aren't supposed to do. The question isn't whether we should be listening. The question is why we aren't already. When comets approach the sun, they begin to shed material from their surfaces. Ice sublimates directly from solid to gas. Dust particles lift off. Trapped volatiles escape. And occasionally, if the comet gets hot enough, trace amounts of metals vaporize from the dust grains embedded in the ice. Nickel and iron appear together. In these outgassing plumes always together, because they form together in stellar processes, exist together in meteoritic material, and sublimate at similar temperatures. The ratio varies slightly from comet to comet, but it follows a predictable pattern. For every atom of nickel you detect, you expect to see about 10 atoms of iron. The previous interstellar comet, 2I, Borisov, followed this rule perfectly. Solar system comets follow it. Every icy body we've observed that shows metal emission follows it. 3. Atlas. The European Very Large Telescope in Chile has been observing this object with its ultraviolet and visual ECEL spectrograph, an instrument designed to split light into its component wavelengths with extraordinary precision. Between August and September, Observers captured spectroscopic data across 6 time periods as the comet moved from 3.1 for astronomical units down to 2.1 for astronomical units from the Sun. In every observation window, nickel emission lines appeared in the spectrum, bright, clear, unmistakable. Iron appeared only when the comet got closer than 2.6 for astronomical units. Before that threshold, nickel without iron. After it, nickel with some iron, but in ratios completely unlike anything seen in other comets. The nickel-to-iron ratio measured orders of magnitude higher than solar abundance ratios, higher than typical cometary ratios, higher than natural geologic processes would produce. The production rate, 3 Atlas was releasing nickel gas at approximately 5 grams per second when first observed. As it got closer and warmed up, that rate increased dramatically. 5 grams per second doesn't sound like much until you consider what it means. That's 430 kilograms per day. Over 3 tons of nickel per week from an object that's supposed to be made primarily of water, ice, and rock. The surface temperature at 2.8 astronomical units, where much of this emission was observed, sits far too low to vaporize silicate, minerals, or metallic grains that would contain nickel and iron. The comet would need to be at least twice as close to the Sun for normal sublimation of refractory materials to occur. Something else is happening. The research team proposed several possibilities. Perhaps nickel exists in a form that releases easily. Nickel tetracarbonyl, a volatile compound that breaks down under ultraviolet light and would release free nickel atoms into the coma. But forming nickel tetracarbonyl requires specific chemistry at specific conditions, specific pathways that aren't common in natural processes. On Earth, we produce nickel tetracarbonyl industrially. It's part of the Mond process used to purify nickel from ore. You heat impure nickel with carbon monoxide at specific temperatures and pressures. The nickel forms gaseous nickel carbonyl. You then decompose it at higher temperatures to deposit pure nickel. The chemical signature of 3 Atlas releasing nickel without corresponding iron mimics the output of this industrial refining process. There's another possibility the researchers mentioned. Perhaps the nickel is embedded in organic compounds or exists as nanoscale particles that respond differently to solar heating than bulk metal grains. Perhaps photon-stimulated desorption, where light directly kicks atoms off the surface, is somehow preferentially releasing nickel. These are plausible natural mechanisms, complex, requiring specific conditions, but possible. Except here's the thing about natural mechanisms: they leave evidence. They require precursor materials. They depend on the comet's formation history, its journey through space, the radiation environment it experienced. 3 Atlas likely formed in the Milky Way's thick disk, a region of older metal-poor stars. Models suggest it spent between 4 and 7 billion years traveling through interstellar space before entering our solar system. During that journey, it would have been exposed to cosmic rays, to background radiation, to collisions with interstellar dust and gas. Could that exposure have created surface chemistry exotic enough to explain the nickel emission? Could the comet have accumulated material during its journey that now, heated by the sun, releases metals in unusual ratios? You'd expect comets that formed around different stars to show chemical differences. Different protoplanetary disks have different compositions. The mix of elements, the ratio of volatiles to refractory materials, the structure of organic molecules, all of this varies based on where and when a solar system forms. But the laws of physics don't change. Nickel and iron still form together in supernova. They still condense together in protoplanetary disks. They still sublimate at similar temperatures. Getting them to separate, to release in dramatically different ratios, requires overcoming fundamental chemical relationships. Unless the nickel isn't sublimating from ice and rock, unless it's being released through a process that involves chemistry we don't typically associate with comets. Loeb, predictably, has pointed out that the observation matches what you'd expect from artificial nickel production. Not that the comet is a factory, but that, if it were a technological object with nickel-based components or a nickel-rich surface coating accumulated during interstellar travel, solar heating could ablate that material. The lack of iron would then simply reflect the composition of whatever is being eroded. The counter-argument is straightforward. Why would an advanced civilization build something out of materials that ablate so easily? If you're designing an interstellar probe to last billions of years, you don't use materials that start vaporizing the moment you get near a star. Unless the vaporization is intentional. Unless releasing a plume of material serves some purpose, schooling, perhaps mass shedding, to adjust trajectory, signal generation, creating a visible marker that can be observed from a distance, or unless the coating that accumulated during the journey wasn't part of the original design. Interstellar space isn't empty. At 60 kilometers per second, even diffuse gas and dust particles impact with significant energy. Over millions of years, a spacecraft would accumulate surface material just like a comet does. If that material happened to be rich in certain elements based on what regions of the galaxy the object traversed, you might see unusual compositions. The Very Large Telescope data doesn't prove any of this. It simply establishes that 3 Atlas is behaving anomalously. The nickel without iron, the extreme production rates, the timing of when different emissions appear, none of it fits comfortably into our models of how comets work. And nickel is just one piece, because while the VLT was documenting metal emissions, the Hubble Space Telescope was capturing images that revealed something even more fundamental, something that challenges the very definition of what a comet is. Comet tails point away from the sun. This is one of the first things you learn about comets, not because they're following the comet's motion, but because they're being pushed by solar radiation and the solar wind. Photons carry momentum. When billions of photons per second strike dust particles and ionized gas molecules, they transfer that momentum outward, creating the characteristic tail that always streams away from our star. Direction is so fundamental to comet behavior that when astronomers spot a comet, they can immediately determine which way the sun lies just by looking at where the tail points. On July 21st, the Hubble Space Telescope captured the highest resolution image yet obtained of 3 Atlas. The comet was 277 million miles from Earth, still inbound toward its October perihelion. The image shows a diffuse glow ahead of the object, pointing toward the sun. The glow is elongated, roughly 10 times longer than it is wide, forming a teardrop or jet-like structure. Behind the object, in the direction where a tail should be streaming, there's nothing. No bright plume, no extended dust trail, just the faint gradient of scattered light fading into background darkness. The glow is an anti-tail. Now, anti-tails aren't completely unknown in solar system comets. Sometimes, under specific geometric conditions, when Earth passes through a comet's orbital plane, we see dust that's been left behind in the comet's orbit, stretching out in front of the comet from our viewing angle. It's an illusion of perspective. But 3 Atlas isn't in this geometric configuration. The viewing angle doesn't support a perspective effect, and the brightness profile of the forward glow doesn't match what you'd expect from orbital dust. David Jewett, an astronomer at UC, who led the Hubble observations, analyzed the surface brightness as a function of distance from the nucleus. In a normal comet coma, brightness falls off gradually. Dust spreads out, dilutes, and the intensity drops following a gentle power law. The forward glow of 3 Atlas drops with a projected power law slope of -3 that corresponds to a 3-dimensional emissivity profile with a radial slope of -4. This is steeper than observed in typical solar system comets, much steeper. A steep falloff suggests that whatever is creating the glow is concentrated near the source and dissipates rapidly. Either the material is extremely fine-grained and quickly pushed away by radiation pressure, or there's active jetting from a specific location on the nucleus, creating a directed plume. Jewett's team interpreted this as dust evaporating from the sunward side of the comet. Solar heating would be strongest on the hemisphere facing the sun. Ice sublimates. Dust lifts off. The dust cloud expands forward before radiation pressure begins to push it back. It's a reasonable interpretation, but it requires the comet to be shedding material asymmetrically, with the sunward side dramatically more active than the rest of the surface. That level of asymmetry is unusual, but not impossible. What's harder to explain is the absence of a dust tail. If dust is being lifted off the surface in quantities sufficient to create the visible forward glow, that dust should persist. Radiation pressure would push it outward. The comet's motion would draw it back into a tail, and we should see something. Unless the dust particles are extremely small, particles smaller than a few hundred nanometers interact so strongly with light that they're blown away from the comet almost immediately, creating a faint haze rather than a distinct tail. However, such minuscule particles are also rapidly destroyed by solar radiation, fragmenting into even tinier pieces until they become virtually undetectable. Otherwise, the majority of what we're observing might not be dust whatsoever, but rather gas. Gas fails to create lasting tails in the manner that dust does. It spreads out. Yet, if gas is primarily responsible for the forward luminosity, this returns us to questions of composition. Which gas, at what emission rate, and what explains such pronounced concentration in a single direction? There exists another hypothesis that Loeb and his colleague Eric Kato investigated in their research paper. Should 3I Atlas be generating its own luminosity rather than merely reflecting solar light, the brightness distribution would appear distinctly different. Internal energy mechanisms, whether originating from radioactive decay or alternative processes, would produce emission that diminishes sharply with distance simply because you're traveling away from the origin point. This concept isn't as outlandish as it may seem. Certain comets display faint airglow within their Kamusi emission, from molecules energized by solar ultraviolet radiation. However, these emissions are thoroughly documented. We understand which wavelengths to anticipate, what intensities to expect, what formations to observe. The Hubble imaging is broadband in nature. It collects light spanning a spectrum of wavelengths. Absent spectroscopic analysis of that particular forward glow, we cannot establish whether it's exclusively reflected sunlight or incorporates some emission element. What we can confirm is that the configuration is irregular, forward-directed, precipitous decline, absent corresponding tail. These characteristics collectively create an image that fails to align with conventional comet models, absent the assumption of exceptional circumstances. And here's what renders it significant. The orientation of this jet or plume, or whatever designation we're assigning it, indicates the direction of travel. The comet is advancing toward the sun, and the luminosity extends forward in that identical direction. If one were attempting to engineer a deceleration mechanism for an interstellar body, expelling material forward would generate thrust in the reverse direction. It's not effective compared to rocket propulsion, but across extended time periods, with sustained mass ejection, it could yield detectable deceleration. 3.1 Atlas has demonstrated no measurable non-gravitational acceleration. Numerous teams have examined its trajectory, assembled thousands of positional measurements, and determined motion compatible with gravitational forces exclusively. Yet that examination has constraints. Minor accelerations beneath approximately 15 meters per day squared would disappear into the observational uncertainty, and the observation period is comparatively brief. The comet was only identified in July. We've monitored it for several months across a segment of its orbit. Were it decelerating gradually, progressively modifying its trajectory through directed mass release, we might not identify it at this stage. Alternatively, the forward jet might be completely natural, the consequence of how ice sublimates from a rapidly rotating nucleus with an asymmetric configuration. The imagery alone cannot provide answers, but combined with the additional irregularities, the nickel emissions, the chemical makeup, the trajectory, it contributes to a pattern where each separate observation permits natural explanation. However, the aggregate picture grows increasingly problematic. You can encounter a comet with atypical chemistry. You can discover one with a peculiar trajectory. You can observe one that outgases asymmetrically. But possessing all of these attributes in a single body, the third interstellar visitor we've ever identified begins to challenge statistical probabilities, particularly when you determine precisely how massive this object genuinely is. When an active comet releases gas and dust, physics requires a reaction, action and reaction. Material expelled from the surface generates thrust, not substantial, but quantifiable. A typical comet might undergo non-gravitational acceleration of several hundred meters per day squared. Throughout weeks and months, this causes the trajectory to diverge from a purely gravitational course. Astronomers utilize these divergences to calculate how much mass a comet is shedding, and consequently how massive its nucleus must be. More massive bodies resist acceleration. A small nucleus ejecting material will deviate noticeably. A large one scarcely moves. Between May 15th and September 23rd, 227 observatories globally monitored 3I atlas, more than 4,000 individual position measurements were accumulated at the Minor Planet Center, the international repository for small body observations. Richard Cloyet, Peter Verez, and Avi Loeb examined this dataset. They matched the observations to a purely gravitational trajectory, determining where the comet should be positioned at each instant based exclusively on the Sun's gravity and planetary perturbations. Subsequently, they searched for deviation. The upper boundary on non-gravitational acceleration emerged as less than 15 meters per day square, perhaps substantially less, perhaps even zero, but definitely below that threshold. This is astonishingly minimal for an active comet that's visibly outgassing the James Webb Space Telescope. Identified carbon dioxide escaping from 3I Atlas at approximately 150 kilograms per second in early August. That amounts to 13 tons daily. As the comet traveled closer to the Sun throughout September, that rate presumably escalated. When you expel mass at high velocity, conservation of momentum dictates that the remaining body experiences a force. The gas departing the surface possesses an outflow velocity around 440 meters per second, as measured by Webb's spectroscopy. Insert the figures. Multiply mass loss rate by velocity. Divide by the comet's mass. The outcome indicates how much the comet should accelerate. If 3I Atlas displayed negligible acceleration despite this continuous mass loss, its nucleus must be sufficiently massive that the thrust becomes undetectable within the observational noise. The calculation produces a minimum mass of 33 billion tons. Consider that figure. The first interstellar object, 1I, Oumuamua, possessed an estimated mass ranging between 10 million and 100 million tons, depending on assumptions regarding its density and shape. The second, 2I, Borisov, likely weighed several hundred million to several billion tons based on its brightness and activity level. 3I, Atlas, measures at least 33 billion tons, potentially more, since that represents merely the lower boundary. It could be 10 times heavier and still satisfy the observations. This renders it 1,000 to 1,000,000 times more massive than the preceding interstellar visitors. And here's where the statistics grow uncomfortable. Models of how interstellar objects form and get expelled from planetary systems forecast a size distribution. Small bodies should vastly exceed large ones in number. This isn't arbitrary. It's founded on what we understand about planet formation, about gravitational interactions, about how material gets launched out of solar systems. For every kilometer-scale object drifting through interstellar space, there should be thousands of objects 100 meters across. For every 100-meter object, thousands more at 10 meters. The distribution follows a power law. When we discovered one, Oumuamua, roughly 100 meters in size, that was anticipated. Small objects are prevalent. They're more difficult to detect because they're faint. But with telescopes scanning the sky continuously, we should locate them. 2I, Borisov, larger and more active, fit the same framework, bigger than Oumuamua, but still within the range of what models predicted we'd encounter. 3I Atlas shatters the pattern. Its minimum diameter, based on that 33 billion ton mass estimate, surpasses 5 kilometers. More realistically, given what we comprehend about cometary densities, it's probably between 5 and 10 kilometers across. Objects this enormous should be extraordinarily uncommon. The models indicate we ought to detect somewhere between 10,000 and 100,000 smaller interstellar objects before encountering one this massive. We've detected 2 Loeb terms, this a major anomaly. The expression understates it. If 3I Atlas truly measures 5+ kilometers across and we're observing it as only the 3rd interstellar object ever identified, either our models of interstellar object populations are catastrophically flawed, or we're exceptionally fortunate to the point of statistical absurdity, or 3I Atlas isn't a random sample from the expected population. The fortunate hypothesis demands believing we achieved a 1 in 10,000 or worse probability, possible but uncomfortable. The flawed model's hypothesis means reconsidering fundamental assumptions about how planetary systems form and evolve, about how objects get ejected into interstellar space, about the mass distribution of debris wandering the galaxy. Not impossible, but it would necessitate major revisions to theories that function well for everything else we observe. The non-random hypothesis suggests 3I Atlas is unusual for reasons beyond statistics. Perhaps it formed through a rare process that generates large objects more frequently than standard planet formation models predict. Perhaps it's a planet-forming seed, as some researchers have suggested a large, solid core expelled early in a solar system's history. Or perhaps it's following an intentional trajectory that brought it here, making its detection not a matter of chance, but of design. That final option is what makes most astronomers uneasy, not because it's impossible, but because accepting it requires abandoning the principle that dictates. We should exhaust natural explanations before invoking extraordinary ones. But here's the tension. At what point do the natural explanations become more extraordinary than the alternative? A comet that's 1 million times more massive than anticipated, that produces industrial metal signatures, that jets material forward with no rearward tail, that glows green without the molecules that cause green luminosity, that aligns with a famous radio signal to within 1% probability, that follows a trajectory passing remarkably close to multiple planets. Each anomaly possesses a potential natural explanation. The combination strains credibility, and we still haven't addressed the single most peculiar aspect of its chemistry, the discovery. That generated headlines precisely because it violated every principle we maintain about what comets contain. On August 6th, the James Webb Space Telescope directed its near-infrared spectrograph at 3I Atlas. Webb operates above Earth's atmosphere, liberated from the water vapor and carbon dioxide that afflict ground-based infrared astronomy. Its instruments can identify molecules that would be invisible to telescopes on the surface. The spectroscopy disclosed carbon dioxide, water, carbon monoxide, and carbonyl sulfide in the comet's coma, all anticipated for an active comet. But the proportions were profoundly incorrect. The carbon dioxide to water ratio measured 8:1 in every other comet ever studied, including the previous interstellar visitor to I Borisov. Water dominates. Carbon dioxide exists as a minor constituent, typically comprising 5 to 20% of the volatile inventory. Water ice forms the bulk of cometary material because water was abundant in the protoplanetary disks where comets formed. 3.1 Atlas inverts this completely. For every molecule of water, there are 8 molecules of carbon dioxide. By mass fraction, the coma is roughly 87% carbon dioxide, 9% carbon monoxide, and only 4% water. This ratio sits 6 standard deviations above the typical value for solar system comets. In statistical terms, that's not an outlier. That's a different population entirely. Martin Cordner, the astronomer who directed the Webb observations, remarked that such elevated carbon dioxide content could indicate the comet formed near the carbon dioxide ice line in its parent protoplanetary disk. This is the distance from a young star where temperatures decline sufficiently for carbon dioxide to condense into solid ice. In our solar system, that line sits farther from the Sun than the water ice line. Objects forming between these two boundaries would be carbon dioxide rich, but even then, you'd expect water to be present as a significant component, not reduced to a mere 4%. Another possibility involves radiation processing. 3.1 Atlas spent billions of years in interstellar space bombarded by cosmic rays. This radiation can modify surface chemistry, fragmenting water ice molecules while leaving carbon dioxide relatively intact. Over sufficient time, you might create a surface layer enriched in carbon dioxide, but that would be a surface effect. Once the comet approaches the Sun and begins shedding material, you'd expect to penetrate through the processed layer and start observing more typical compositions underneath. The spectroscopy shows no indication of this transition. The carbon monoxide ratio adds another puzzle. At 1.4 times the water abundance, it's elevated, but not as dramatically as the carbon dioxide. Carbon monoxide is even more volatile than carbon dioxide. It sublimates at lower temperatures. If the comet was simply warming up and releasing ices in order of volatility, carbon monoxide should appear first and in high abundance. Instead, it's carbon dioxide that dominates, with carbon monoxide as a secondary component. This chemistry suggests formation conditions unlike anything in our solar system. Either the comet originates from a protoplanetary disk with radically different composition than the one that formed our planets, or it underwent processes during its journey that transformed its makeup into something we've never encountered. And then there's the polarization. When light scatters off dust particles, it becomes polarized. The degree and direction of polarization depends on the size, shape, and composition of the particles, as well as the angle at which you're observing. Astronomers use polarization to infer properties of cometary dust that are difficult to measure directly. A team led by Zach Gray observed 3I Atlas through polarizing filters over several weeks. They measured polarization as a function of phase angle, the angle between the Sun, the comet, and Earth. The results were unlike any object in the solar system. 3I Atlas showed extreme negative polarization. At small phase angles, the polarized light was oriented perpendicular to what every other comet, asteroid, and dusty object displays. The magnitude of this negative polarization exceeded anything in the existing database. Negative polarization can occur when light scatters off particles with specific optical properties, but achieving the degree observed requires unusual combinations of size, composition, and structure. The dust grains would need to be larger than typical cometary dust, perhaps with complex internal structure or unusual refractive indices. Or the scattering isn't happening in the way we typically model. If the dominant light source isn't scattered sunlight, but includes emission from the object itself, polarization signatures change. Fluorescence from gases can produce polarization patterns different from pure dust scattering. But again, that requires explaining what's emitting light and why. The polarization study. The inverted chemistry from Webb, the carbon chain depletion that somehow still allows a green glow. These observations combine to paint a picture of an object that violates expectations at every level. You can construct scenarios where each finding individually makes sense. A comet from a carbon dioxide-rich formation region. Dust with unusual optical properties from extended radiation exposure. Surface chemistry altered by billions of years in space. But explaining all of them simultaneously in a single object requires stacking unlikely conditions on top of each other. The comet would need to have formed in exactly the right location to be carbon dioxide dominated, then been ejected at exactly the right time to spend billions of years in interstellar space accumulating radiation damage, then happen to collect dust during that journey with optical properties unlike anything we typically see, then entered our solar system on a trajectory that brings it unusually close to multiple planets. The more specific the required conditions become, the less likely the scenario. And there's one more detail that deepens the mystery: the cyanogen detection. Cyanogen is a carbon-nitrogen compound. It's not uncommon in comets, but its presence is interesting because early observations detected it in 3I Atlas, while simultaneously showing a strong depletion of other carbon chain molecules like dicarbon and tricarbon. Luis Salazar Manzano at the University of Michigan analyzed spectra from Kitt Peak Observatory. His team found evidence for cyanogen emission before the comet was close enough to the Sun to be strongly active. This suggests cyanogen was present in volatile form near the surface, easily released with minimal heating. But cyanogen production in comets typically correlates with the presence of complex organic molecules and carbon chains. Finding one without the others is unexpected, like discovering smoke without fire. Unless the chemistry isn't following the pathways we assume. Unless the molecules weren't created through the standard processes of comet formation and evolution. Unless they were introduced through mechanisms we haven't considered. The chemical signature of 3I Atlas reads like a comet designed to confuse. Every measurement reveals properties that technically could be natural, but collectively strain the boundaries of what natural processes produce. And while chemists debate isotope ratios and spectroscopists argue over emission line profiles, Avi Loeb has been calculating something else. Entirely something that makes the chemistry question secondary to a more immediate concern about what this object might do next. Began with a simple geometric calculation. 3I Atlas passed within 29 million kilometers of Mars on October 3rd, but that's not the closest it gets to Mars' orbital path. The minimum orbit intersection distance, a measure of how close one object's trajectory comes to another's complete orbital paths, sits at just 2.7 million kilometers. 2.7 million kilometers sounds vast. It's roughly 7 times the distance between Earth and the Moon. But in orbital mechanics terms, especially for an object traveling at 60 kilometers per second, it's remarkably close. Close enough that a small adjustment in velocity could bring the comet into direct contact with Mars. Loeb calculated the numbers. A trajectory change of 10 to 15 kilometers per second applied during September would shrink that closest approach distance to zero. The comet would impact Mars, or at minimum pass within the planet's atmosphere. Now, comets don't make trajectory changes that large. The outgassing thrust from a natural comet might produce velocity changes of a few hundred meters per second over months. Getting to 10 or 15 kilometers per second requires either a catastrophic fragmentation event or active propulsion. But here's what caught Loeb's attention. If 3I Atlas isn't a single object, if it's accompanied by smaller components, those components don't need to match the main object's velocity. A mothership releasing smaller probes can impart significant relative velocity. The probes separate, following slightly different trajectories. While the main object passes Mars at 29 million kilometers, a probe with the right velocity vector could reach the planet. The Webb telescope measured the outflow velocity of gas leaving 3I Atlas at 440 meters per second. That's the speed of material naturally vaporizing from the surface. But if something were deliberately ejected, if a probe separated from the main body using mechanical force rather than thermal evaporation, it could achieve much higher speeds. A velocity of 10 kilometers per second isn't unreasonable for a separation maneuver. It's well within the capability of conventional rocket propulsion. Even a simple spring-loaded release mechanism could impart a few kilometers per second to a small object. So Loeb asked if 3I Atlas released precursor probes in September, could they reach Mars? The answer is yes. Depending on timing and direction, a probe could arrive at Mars anywhere from a few days to a few weeks after separation. Now, we need to think about what that means practically. The high RISE camera on Mars reconnaissance orbiter was looking for 3I Atlas. It was calibrated to detect an object 5 to 10 kilometers across at 29 million kilometers distance. But HiRIC was designed to image Mars's surface. It can resolve features down to 30 centimeters. If a smaller object, say 100 meters, across passed closer to Mars, within even a few 100,000 kilometers, HiRIC might detect it. Except HiRIC was pointed at the expected position of the main comet. If a precursor probe came from a different angle, took a different path, it could approach Mars unobserved by the spacecraft specifically watching for 3I Atlas. The Perseverance rover's sky observations become more interesting in this context. Those images showing possible multiple objects, the ones Stefan Burns and others analyzed, were taken during a window when both the main comet and any potential companions might be visible. If there were multiple fast-moving objects in those images, if that's not just processing artifacts or background noise, we might be seeing evidence of a dispersed system rather than a single compact nucleus. Loeb took the calculation further. He considered what happens after perihelion after the comet swings around the Sun and emerges on the other side. The object will be hidden from Earth-based observation from late October through most of November. It reaches perihelion on October 29th, at a distance of 202 million kilometers from the Sun. During that closest approach, it will be experiencing maximum solar heating, maximum radiation pressure, maximum stress on any structural components. If it's a natural comet, this is when we'd expect to see dramatic changes, increased activity, possible fragmentation. The nucleus could split, releasing fresh ice that dramatically brightens the coma. Outgassing rates could spike as subsurface volatiles reach critical temperatures. If it's something else, if it's capable of maneuvering, perihelion offers a strategic opportunity. The gravitational assist from passing close to the Sun could be used to alter trajectory. A small velocity change at perihelion translates to large position changes months later. This is how spacecraft use gravity assists to reach distant destinations efficiently. Loeb noted that, with appropriate thrust at perihelion, 3I Atlas could adjust its path to intercept Earth. The object will be traveling retrograde, opposite to the direction planet's orbit. This geometry offers advantages for an intercept trajectory. You're not chasing a target. You're timing the collision between two objects moving toward each other. A velocity shift of 30 to 40 kilometers per second. October could bring 3I Atlasor components of it too. Earth between late December and early January is 30 to 40 kilometers per second, achievable for a natural comet. Absolutely not. For a spacecraft with propulsion, it depends on the mass and the engine. Chemical rockets would struggle with those numbers for something as massive as 3I Atlas. But we're talking about technology that potentially crossed interstellar space propulsion systems we can barely imagine. Loeb was careful in how he phrased this. He didn't claim 3I Atlas would maneuver toward Earth. He pointed out that the opportunity exists, that if the object has capability, this is when and how it would use it. And then he added something that got picked up by every news outlet covering the story. If 3I Atlas maneuvers toward Earth when it reappears from behind the Sun, financial markets may crash. Think about what that statement implies. Not just the immediate panic from news of an object heading toward our planet, but the deeper implications. Confirmation that we're dealing with technology, that something artificial crossed interstellar space and is now approaching Earth, that we're not alone, and that whatever is out there knows we're here. Markets crash on uncertainty, on fundamental shifts in how we understand the world. The discovery of artificial interstellar technology would be the most profound uncertainty in human history. Even if the object posed no direct threat, even if its intentions were entirely benign, the knowledge that advanced civilizations exist and can reach our solar system would reshape every assumption underlying our economic, political, and social systems. Loeb's statement wasn't fear-mongering. It was recognition that the implications extend far beyond astronomy. This is why the Mars observations matter so much. This is why the silence from NASA and ESA feels significant, because right now, 3I Atlas is approaching the point where if it's going to do something unexpected, this is the window. And we won't know what happened until it emerges from solar occultation weeks from now, potentially having changed course, potentially having released objects we can't track, potentially having demonstrated capabilities that force us to abandon the comfortable assumption that it's just an unusual comet, the Trojan horse. Loeb calls Eton innocent-looking visitor that could carry devastating consequences, hidden within its apparently natural exterior. Loeb created a scale. He calls it the Loeb scale, a ranking system from 0 to 10 that quantifies how likely an object is to be artificial rather than natural. 0 means definitively natural, a chunk of ice and rock following predictable physics with chemistry that matches known processes. 10 means definitively artificial, an object that displays unambiguous technological signatures, that maneuvers in ways requiring propulsion, that emits signals or exhibits structure impossible to explain through natural means. Most objects score 0. Asteroids, comets, meteoroids, all the debris wandering through space scores 0 because nothing about them suggests technology. 1. Ia Oumuamua, the first interstellar visitor. Loeb ranked somewhere between 3 and 5, depending on which observations you emphasize. Its unusual shape, its non-gravitational acceleration without visible outgassing, its tumbling motion, these features pushed it above 0, but not high enough to claim certainty. 3i Atlas Loeb currently ranks at 4, not 0 because the anomalies are too numerous. The trajectory alignment with planets, the chemical inversions, the nickel without iron, the forward jet with no tail, the mass discrepancy. Each individually might be natural, but collectively they elevate the probability of something more. Not 10, because we lack definitive proof. No detected radio signals, no observed maneuvers, no photographs showing geometric structures. The object still behaves enough like a comet that natural explanations, however strained, remain possible, for sits in the uncertain middle, more likely than not to be natural, but with enough unusual features that the artificial hypothesis can't be dismissed. But that ranking could change dramatically based on what happens over the next few weeks. October 29th. The comet reaches its closest point to the Sun at roughly 1.4 astronomical units just inside Mars' orbital distance. At that moment, from Earth's perspective, it will be directly behind the Sun. The Sun's angular diameter in our sky is about half a degree. 3i Atlas will pass within that glare zone. Ground-based telescopes can't observe it. Space-based observatories like Hubble and Webb need to avoid pointing too close to the Sun to protect their sensitive instruments. We go blind. The blackout extends from late October through most of November. The exact dates depend on viewing geometry and how bright the comet becomes. But, conservatively, we lose direct observation for at least 3 weeks, free weeks where the object experiences peak solar heating, where any thermal stresses reach maximum, where if it's technological, it has privacy to do whatever it's designed to do. When it emerges, we'll be looking for changes. Brightness is the first indicator. If the comet fragments or undergoes a major outburst, it will brighten significantly. Solar system comets sometimes increase in brightness by several magnitudes during perihelion passage. If 3i Atlas does the same, it suggests natural processes are dominant. If it doesn't brighten, if it remains relatively stable or even dims, that's interesting. It might indicate a more durable structure, less vulnerable to thermal stress than typical comets. Trajectory is the second indicator. If the object emerges on a path consistent with gravitational predictions, following the orbit calculated from pre-perihelion observations, that supports the natural interpretation. If there's any deviation, any change in velocity or direction not explained by gravitational perturbations that moves it up the lobe scale quickly, spectroscopy will reveal compositional changes. Did the surface chemistry shift? Are new materials exposed? Is the ratio of volatiles different from what we measured before? And structure when 3I Atlas becomes visible again in early December. Telescopes will immediately photograph it. Does it look the same? Is the forward jet still present? Is there evidence of fragmentation or splitting? Meanwhile, Low is doing more than simply computing probabilities. He is monitoring the heavens. The Galileo project runs 3 observation stations, one located in Massachusetts, another in Pennsylvania, and a third in Nevada. These facilities are outfitted with wide-field cameras, infrared detection systems, and automated algorithmic sensors, engineered to recognize aerial phenomena that fail to correspond with standard aircraft or natural celestial bodies. The project's principal objective centers on unidentified anomalous phenomena referred to as UFOs. However, with 3I Atlas nearing perihelion, Low has implemented a specialized surveillance protocol. Should the object prove to be a mothership, should it deploy smaller reconnaissance probes toward Earth during its solar swing, those probes would make their arrival weeks to months afterward. The December through January timeframe establishes the window during which unexplained aerial activity could potentially intensify. The Galileo project's instrumentation will operate without interruption, recording any anomalies, analyzing for patterns, searching for objects traveling at velocities exceeding satellites, exhibiting flight behaviors beyond existing aerospace capabilities, manifesting in quantities or with chronological patterns that align with 3I Atlas's perihelion transit. This sounds like speculative fiction. It represents science fiction in the manner that we are examining scenarios extracted from imaginative narratives. Yet the distinction lies in our approach. We are pursuing this with authentic data, genuine calculations, actual objects that we can capture photographically and quantify. Should Low prove incorrect, should 3I Atlas turn out to be merely an atypical comet, and all the irregularities possess mundane explanations, the Galileo project will register nothing extraordinary. The object will reappear from behind the sun, marginally more luminous, potentially fractured, adhering to its forecasted trajectory. The nickel signatures will receive explanation through some unconventional chemical process. The trajectory correspondence will be understood as selection, bias regarding which interstellar objects capture our attention life proceeds as before. Should he prove correct, should even a fraction of his hypothesis hold true, December transforms into one of humanity's most consequential months, not due to invasion narratives or aggressive intentions. Low exercises caution to circumvent that characterization. Even manufactured objects may represent benign scientific instruments from civilizations harboring no desire for intervention. Rather, because verification alters everything, every presumption about our cosmic position undergoes revision. Every inquiry about whether we exist in isolation receives its answer. Every determination about resource distribution, about how we conceptualize our destiny, gets formulated within a framework where we comprehend that traversing interstellar distances is achievable, that alternative intelligences are extant. that we occupy, in the most fundamental sense, no exceptional status. Indeed, the JUICE spacecraft, presently en route to Jupiter, will conduct observations of 3I Atlas during late November. Throughout the period spanning November 2nd through the 25th, JUICE will direct its instrumentation toward the comet immediately following perihelion. When it emerges from the Sun's overwhelming radiance, yet remains extraordinarily active, JUICE transports cameras, spectroscopic equipment, and particle detection instruments. Its position places it at a greater distance from the comet than Mars achieved. Yet it possesses the benefit of observing during maximum activity, when identifying signatures manifest most powerfully. The information from JUICE will not reach us until February. The spacecraft occupies the far side of the Sun relative to Earth, utilizing its high-gain antenna as thermal protection, transmitting through a less efficient backup communications channel. Therefore, we must wait months for those observations to transfer and undergo processing. Nevertheless, they are forthcoming, and they may reveal what 3I Atlas was experiencing while concealed from Earth. Its appearance during its most energetic phase, whether any transformations occurred that demand our comprehension. For the present moment, though, we remain in darkness, both literally and metaphorically. The object that has been confounding astronomers for months is approaching invisibility, obscured behind the overpowering brilliance of our star, engaging in whatever activities occur beyond observation. And upon its return, should it return altered, should it display any indication of having executed something deliberate, Lowe's assessment advances from 4 to 5, perhaps beyond, and the questions we have been posing about whether it might be artificial transition to questions about its objectives and our appropriate response. There exists a conventional cadence to how space agencies disseminate discoveries. Press communications undergo preparation. Scientists participate in media interviews. Unprocessed data populates accessible repositories. Social media channels distribute notable findings. The framework is structured to maintain transparency, to cultivate public engagement, to validate the financial support that enables these missions. When that cadence fractures, when scheduled observations transpire, yet findings fail to materialize, when inquiries receive deflection through ambiguous declarations about continuing analysis, observers take notice. NASA's official documentation for 3I Atlas enumerates assets that observed or intend to observe the object: Hubble, Webb, TESS, SWIFT, SPA, Perseverance, Mars Reconnaissance Orbiter, Curiosity, Europa Clipper, Lucy, Psyche, Parker, Solar Probe, Punch, SOHO, and ESA's JUICE. It constitutes an remarkable assemblage. Virtually every operational space telescope and planetary mission received targeting toward this object at some juncture. Yet the data publications fail to correspond with the observation timeline. Webb spectroscopy from August materialized promptly, released as a preprint within weeks. Hubble's July imagery became publicly accessible. SPHRX findings regarding carbon dioxide emissions received distribution. Then October arrived, and the flow ceased. The Mars observations spanning October 1st through 7th should have represented the simplest to release. Mars orbital platforms routinely render their imagery public within days. The HiRIC website characteristically updates with fresh Mars surface photographs every few days, occasionally daily during intensive observation initiatives. Yet nothing from the 3I Atlas encounter has surfaced. ESA functions under distinct administrative frameworks from NASA-divergent funding streams, alternative oversight structures, separate public communication mandates. When both agencies adopt simultaneous silence concerning the identical target, it implies coordination. Coordination may signify collaboration scientists from both organizations working collectively, concurring to postpone until comprehensive data undergoes analysis before issuing statements. This approach proves reasonable for complex observations where preliminary findings might suffer misinterpretation. Alternatively, coordination may indicate consultation and covering, something unanticipated that necessitates deliberation about presentation, methodology, contextual provisions, supplementary verification, completion before proceeding publicly. The silence from Simeon Schmaus, the astrophotographer who asserted observing early glimpses in October 1st imagery, contributes another dimension. Amateur observers characteristically share their discoveries enthusiastically. The community flourishes on rapid discourse, on crowdsourced authentication, on cooperative examination. When someone grows silent following an intriguing assertion, it typically indicates one of two scenarios. Either they identified an error and experience embarrassment, or they uncovered something significant and are constructing a more comprehensive presentation. Schmaus has not withdrawn his observations. He has not issued corrections. He simply discontinued commentary. Meanwhile, amateur astronomers persist in working with whatever information remains available. The publicly distributed Perseverance images from those October evenings remain obtainable. Anyone possessing image processing capabilities can retrieve them, composite them, search for mobile objects. Multiple independent analysts have now replicated Stefan Burns's identification of at least one rapidly moving object consistent with 3I Atlas. The discussion concentrates on whether supplementary objects exist. Some perceive them distinctly. Others ascribe the apparent additional luminous points to processing artifacts, to cosmic ray impacts that coincidentally manifest near the comet's trajectory to background asteroids. Without the high-resolution information from HiRIC and the ESA orbiters, without official verification or refutation, the question persists unresolved. What we are witnessing constitutes a pattern. Official channels constrained by review procedures and institutional prudence. Amateur observers bridging the void with fluctuating degrees of precision and dependability, and an object that continues producing more inquiries than resolutions. Consider what remains unknown despite months of surveillance. The precise dimensions of the nucleus span from under 1 kilometer to exceeding 10 kilometers, contingent upon assumptions about albedo and whether we are observing predominantly the nucleus or an extended dust envelope. The rotation velocity. Certain observations imply rapid rotation. Others reveal no evident periodicity. Comprehending its spin rate informs us about structural resilience, about whether it represents a singular solid mass or a loose conglomerate. The outgassing source. Regions is material venting from isolated jets or from extensive surface areas. Isolated jets suggest localized volatories or structural characteristics. Widespread emission suggests more uniform surface constituency. The fragmentation degree, if any, has the nucleus divided into multiple fragments. Do companion fragments travel alongside the primary body, or does it maintain structural integrity? These constitute fundamental questions the Mars observations were intended to resolve. High RIC at 30 centimeters resolution should readily distinguish between a singular compact object and a fragmented or multi-component configuration. The spectroscopy from Mars Express and ExoMars should expose regional compositional variations, should they exist. The instruments functioned appropriately. The observations were executed. The data resides somewhere within agency archives. We simply are not accessing it. Innocent explanations exist. Data pipelines genuinely overwhelmed by technical complications. Scientists conducting exhaustive analysis before formulating statements. Bureaucratic delays unconnected to the observation content. Less innocent explanations exist. Uncertainty regarding how to characterize unexpected discoveries. Consultation about whether preliminary observations merit broader discussion before formal publication. Institutional reluctance to advance claims that might subsequently require humiliating retractions and concerning explanations exist. Discovery of features that challenge comfortable presumptions. Evidence of configurations or behaviors that fail to conform to natural classifications. Observations that, if released without context, would generate precisely the variety of speculation and alarm that agencies labor diligently to prevent. We cannot determine which category applies. That constitutes the predicament. The information void creates a vacuum that speculation occupies. What we can state with certainty is that the forthcoming weeks matter tremendously. 3I Atlas will emerge from behind the sun during late November or early December. Ground-based telescopes will immediately capture it photographically. Amateur astronomers will maintain vigilance. Professional observatories will designate observation time. Should it appear identical? Should its trajectory conform to predictions? Should its luminosity and spectral characteristics remain consistent with what we measured previously? The natural comet explanation strengthens considerably. Should anything have transformed? Should evidence exist of maneuvering or structural modification or unexpected brightening or novel compositional signatures, the artificial hypothesis acquires support. JUICE will observe it during late November throughout peak post-perihelion activity. Europa Clipper, currently traveling toward Jupiter, might also secure observations depending on geometric configurations and mission priorities. These spacecraft perceive the comet from angles and distances unavailable to Earth-based instrumentation. Their data will eventually arrive, eventually undergo processing, eventually inform our comprehension. Yet eventually is not now. Presently, we exist in a gap between what has been observed and what has been communicated. A gap between amateur discoveries and official confirmation. A gap between the questions we are posing and the answers that exist somewhere in data files we cannot access. And while we wait within that gap, 3I Atlas continues its voyage, approaching the sun, heating intensively, becoming increasingly active, potentially executing actions we will not comprehend until weeks hence, when it reappears and we observe what transformed. Therefore, here we and waiting, monitoring an empty expanse of sky where something extraordinary remains hidden behind our sun. 3I Atlas exists out there at this very moment, nearer to our star than it has been across billions of years, absorbing gigawatts of solar radiation, potentially fragmenting, potentially maneuvering, potentially engaging in nothing more dramatic than what comets have performed since the solar system's formation. We have traced its path from the outer boundaries of space, calculated its location when the WOW signal reached Earth, measured the impossible ratios within its chemistry, documented the metals that should not exist there, charted the tail that directs the incorrect direction. We have tallied the statistical improbabilities, accumulated the anomalies, and arrived at a position where certainty feels impossibly remote. Perhaps it is merely a cometon, unusual specimen, admittedly, yet ultimately a natural object adhering to natural principles. The anomalies will achieve resolution. The absent data will surface and provide clarification. December will arrive, and the object will appear precisely as anticipated, marginally more luminous, following its predicted trajectory, confirming that the universe still maintains coherence. Or perhaps we are monitoring something that will rewrite every assumption we maintain about our position in the cosmos. Regardless, the upcoming weeks will inform us, and we will be present when they do. Thank you for remaining engaged with this narrative, for pursuing these questions into uncertainty, for demonstrating willingness to dwell with mystery rather than demanding facile answers. Should you find this valuable, consider expressing approval and subscribing so you are present when the object emerges, and we finally comprehend what we have been observing. As always, this content serves educational and entertainment purposes. The science maintains authenticity. The observations carry documentation, yet the interpretations remain speculative. We are exploring possibilities, not advancing definitive assertions. Conduct your own research. Question everything, including what you have encountered here. For now, 3I Atlas moves in silence behind the sun. December approaches. The amateur telescopes stand ready. The professional observatories have allocated time. The Galileo Project instrumentation is recording. And somewhere out there in the darkness, an object from another star prosecutes its journey, indifferent to our questions, our theories, our hopes, and fears regarding what it might represent. Sleep peacefully, dream of distant stars, and remember that the universe has perpetually been stranger than we envisioned. Good night. Picture this, right now, at this precise moment, 620 light-years away, a planet equivalent to Jupiter's size is consuming, not gradually, not cautiously, but with violence. 6 billion tons of gas and dust every solitary second, streaming into something that should not exist, something that obscures the boundary between what we designate a planet and what we designate a star. Meanwhile, nearer to home, on a world we have examined for decades, a robot the dimensions of a car has uncovered something within a rock that just might be the fingerprint of alien life. And in laboratories spanning Earth, scientists have just demolished a barrier that has persisted throughout quantum computing's entire history, constructing a machine capable of running indefinitely, theoretically speaking, unveiling doors we believed were decades distant. But here is what renders this week genuinely strange. While we are generating these cosmic discoveries, We are simultaneously discovering that our own bodies harbor secrets we never suspected. Fat tissue, the variety we carry daily, has been caught red-handed, dispatching chemical messengers directly into our brains. Messengers that may be constructing the very plaques that steal our memories. And should we journey back sufficiently far in time, before any of this mattered, before humans, before dinosaurs, before the first tree ever flourished, there existed a kingdom that dominated this planet for nearly 1 billion years. Not animals, not plants, fungi. The concealed architects that constructed the world we inherited. This is not science fiction. This is This Week. Should you find yourself drawn into these mysteries, activate that like button and subscribe. Then inform me in the comments where you are listening from, what time it is there, and which of these discoveries shakes your understanding of reality most profoundly. And should you wish to help our community expand, share this on X, Facebook, Reddit, or your messenger. Thank you for consistently supporting us on the 23rd of July, 2024. A machine designated Perseverance pressed a drill bit into a rock on Mars. The rock possessed a name, Sheava, falls selected by the team back on Earth, who had been monitoring this particular stone for months. They maintained reasons. The rock occupied the edge of what formerly was a river valley, a channel that once transported water rushing into a crater that contained a lake more than 3.5 billion years ago. Yet it was not the location alone that caused them to halt. It was the pattern adorning the surface spots. Dark circles with pale rings scattered across the reddish stone, like the markings on a leopard's fur. No one had witnessed anything quite like it previously. The drill collected a core sampler, cylinder of rock, approximately as thick as a pen, sealed it inside a tube for potential return to Earth. Then the authentic work commenced. The rover transported instruments capable of peering into the rock's chemistry without opening the tube. What they discovered sent ripples through the scientific community that continue spreading today. The spots contained iron and phosphate. Between the pale bands of calcium sulfate, there appeared traces of hematite, the mineral that imparts Mars its red coloration. Yet here, within this rock, something had transformed the red to white. That variety of chemical reaction releases iron and phosphate, and those reactions can furnish energy, the variety of energy that microbes utilize. On September 10, 2025, a paper materialized in the journal Nature. The authors had invested a year examining the data, executing tests, checking and rechecking their findings. They described the presence of 2 specific minerals, vivianite and grigotiron, phosphate and iron sulfide. On Earth, these minerals form in oxygen-depleted environments where microbes are consuming organic matter, where life is utilizing chemistry to survive. The patterns corresponded. The chemistry corresponded. Everything about this rock suggested a process that on our planet would be unmistakably biological. NASA's acting administrator conducted a press conference. After a year of review, he stated, they could not identify another explanation. This very well could be, he informed the world, the clearest sign of life we have ever discovered on Mars. Not proof, not yet, but the closest approximation to it we have ever held in our robotic grasp. The media exploded. Headlines proclaimed alien microbes and ancient Martian life. Yet the scientists exercised greater caution. They employed a term that sounds awkward but carries enormous significance. Potential biosignature, a thing that might have been produced by life but requires additional study before anyone can state with certainty. Here is where the narrative takes a frustrating turn. The sample resides inside Perseverance's interior, sealed in its tube, alongside 24 other samples collected from different locations across Jezero Crater. To know definitively what created those leopard spots, scientists need to transport that rock home. They need to examine it with instruments far more sensitive than anything we can transmit to Mars. They need mass spectrometers and electron microscopes and tools that occupy entire laboratories. There exists a program designed to execute precisely this. It is designated Mars Sample Return. Yet the program faces trouble. The projected cost inflated to somewhere between $8 and $11 billion. The timeline extended to 2040 or beyond. Then came changes in political administration, shifts in priorities, budget constraints. As of today, Mars Sample Return exists in a kind of limbo, neither deceased nor fully alive. Therefore, we possess a rock on Mars that might contain evidence of ancient life, and we possess no clear pathway to transport it home, 620 light-years from Earth. In the constellation Chameleon, there exists an object that should not behave the manner it does. It possesses a designation rather than a name. Chia J11.077,626, a string of numbers and letters that astronomers utilize to catalog things they discover in the cosmos. This object maintains mass somewhere between 5 and 10 times Jupiter's mass, our solar system's giant. That mass positions it firmly in the category we designate planets. Yet, it does not orbit a star. It drifts alone through space, one of what we believe are trillions of rogue planets wandering the galaxy, untethered, floating in the darkness between stars. For years, scientists thought these rogues were cold, quiet, dormant objects that formed around a star and were expelled, or perhaps collapsed from gas clouds too small to ignite fusion, forever dim and unremarkable. CHIAJ 1107 proved them wrong. In the spring of 2025, astronomers directed the European Southern Observatory's Very Large Telescope toward this object. They witnessed something astonishing. A young world still surrounded by a disk of gas and dust, the leftover material from its formation. The disk was feeding the planet gradually through a process designated accretion, material falling onto the surface, adding to its mass bit by bit. This is normal. This is how planets grow. Then, by August, everything transformed. The planet began devouring its disk knot. The accretion rate spiked 8 times faster than it had been merely months before. 6 billion tons of material every single second, pouring into this lone world floating in the void. To position that in perspective, imagine the entire mass of Mount Everest disappearing into this planet every few seconds. For at least 2 months, this feeding frenzy persisted, and when the paper was published on October 2nd, 2025, it was still continuing. The lead researcher, a scientist named Victor Almendrosabad, stated something that captures the strangeness perfectly. People may think of planets as quiet and stable worlds, he explained, but with this discovery, we see that planetary mass objects freely floating in space can be exciting places. Exciting is perhaps an understatement. What Chia J1107 is executing has only been observed previously in young stars and brown dwarfs objects, massive enough to maintain complex magnetic activity. This is the strongest accretion episode ever recorded for a planetary mass object ever in the entire history of astronomy. Here is where it becomes stranger. The team detected signs of magnetic fields driving this infall of material-strong magnetic fields, funneling gas and dust toward the planet's surface like invisible highways in space. This is a process we associate with stars, not planets. Stars possess the mass and internal dynamics to generate powerful magnetic fields. Planets, especially rogue planets drifting alone, should not. Yet here it is occurring, observable, undeniable. The discovery also revealed water vapor in the planet's atmosphere during the burst, and hydrocarbon molecules that shifted in configuration as the feeding, intensified signatures of heat and turbulence, reorganizing the disk's chemistry. Scientists are now posing a question they thought they had answered. Where do rogue planets originate? The two main theories have been ejectionware. A planet forms around a star and gets expelled by gravitational interactions or direct collapse, where a gas cloud in space collapses under its own gravity, but never acquires sufficient mass to become a star. Should ejection be the answer? These planets should be cold, dead, their formation disks long vanished. Yet Chia J1107 still possesses its disk. It is still growing, behaving like something that formed in place, condensing from a cloud just like a star would, only ceasing short of the mass required for fusion. This blurs a line we thought was clear. What constitutes the difference between the smallest stars and the largest planets? We defined it by fusion, by whether an object can sustain hydrogen burning in its core. Yet, if objects in the planetary mass range can form like stars, grow like stars, and utilize magnetic fields like stars, then perhaps the line is not as sharp as we believed. Perhaps there exists a spectrum, a gradient between planet and star, and rogue worlds like Chia J1107 inhabit somewhere in the middle. Defying our categories, the researchers believe we are witnessing planet formation transpire in real-time, observing a world construct itself in the darkness between stars. And the process is far more dynamic, far more violent than anyone predicted. Inside a laboratory at Harvard University, there exists a machine that has been operating for over 2 hours. This might not sound remarkable until you comprehend what the machine is. It is a quantum computer. And for the entire history of quantum computing, these devices have maintained a fatal flaw. They stop not because someone deactivates them, but because the quantum bits, the qubits that make them function, simply vanish. They decohere, as physicists state, meaning they lose their quantum properties and become useless. Early quantum computers could operate for milliseconds. The most advanced machines extended that to around 13 seconds. Then they had to restart, reset, begin again. The Harvard team, led by a professor named Mikhail Lukin, constructed something different. In September of 2025, they published their findings in the journal Nature. Their quantum computer possesses 3,000 qubits, and it can operate continuously without stopping, without restarting, for as long as they choose to keep it powered. Theoretically, it could operate forever. This is not an incremental improvement. This is a fundamental breakthrough that transforms what quantum computers can accomplish. Here's the problem they solved. Quantum computers function by manipulating atoms, or subatomic particles, maintaining them in delicate quantum states where they can represent multiple values simultaneously. This is what grants quantum computers their power, their ability to solve certain problems exponentially faster than classical computers. Yet these quantum states are fragile. They require extreme cold, often near absolute zero. They require isolation from vibrations, from stray electromagnetic fields, from anything that might disturb them. And even with all that protection, the qubits eventually fail. They leak information, they collapse, the quantum state dissolves, and the computation terminates. The Harvard team invested 5 years working on this problem. They developed a method utilizing what they designate an optical lattice conveyor, belt and optical tweezer stools made of focused laser light that can grasp individual atoms and move them around with extraordinary precision. The breakthrough was determining how to replenish the qubits while the machine is operating. As qubits exit the system, new atoms are injected to replace them. The machine can add 300,000 atoms per second, far exceeding the rate at which qubits are lost. There is now fundamentally nothing limiting how long these quantum computers can operate. One of the researchers, a man named Tout Wang, stated something striking in an interview. There is still a way to go to scale from where we are now, but the roadmap is now clear based on the breakthrough experiments we've done here at Harvard. Clear roadmap. Words matter in a field where progress has been uncertain and timelines have repeatedly slipped. Another collaborator, a physicist from MIT named Vladin Vuletic, was even more specific. Before this, it was believed that continuously running quantum computers were at least 5 years away. Now it seems much closer, more on the horizon of 2 to 3 years. Consider what that signifies. Within 2 to 3 years, we might possess quantum computers that operate like the classical computers. We use daily not machines that run for seconds and restart, but machines that remain active, that accumulate results, that can tackle problems requiring long, sustained computation. The implications ripple across dozens of fields. Drug discovery, where quantum computers could simulate molecular interactions that are impossible to calculate classically. Cryptography, where they could break encryption schemes that protect global communications. Artificial intelligence, where they could optimize neural networks in ways we cannot currently achieve. Material science, financial modeling, climate prediction, any domain where complexity exceeds traditional computing's reach. Yet there is another layer to this narrative. Google also generated news in the quantum world recently, using a 58-qubit quantum computer to create and observe something designated a FOK, topologically ordered stataphase of matter, that was theorized but never seen. It exists only when a quantum system is driven rhythmically, periodically, creating a non-equilibrium state that cannot be captured by traditional physics. They watched exotic particles transform in real time, confirming theories about how matter behaves when pushed far from equilibrium. These are the varieties of experiments that quantum computers enable, not just rapid calculations, but entirely new methods of exploring physics itself. There is something transpiring inside your body right now that scientists have only just discovered. Your fat tissues, adipose that cushions your organs and stores energies not sitting quietly. It is talking not in words, obviously, but in chemical messages. Tiny packages wrapped in membranes that travel through your bloodstream. These packages are designated extracellular vesicles, and they carry cargo, lipids, proteins, genetic instructions. They slip through the walls of blood vessels. They cross barriers that most molecules cannot penetrate, and some of them, researchers have now proven, make it all the way into your brain. A team at Houston Methodist, led by a scientist named Stephen Wong, published their findings on October 3, 2025. They collected fat tissue samples from people who were lean and people who were obese, isolated the vesicles these tissues released, and examined what was inside. The lipid cargo was different. Specific fat molecules were more abundant in vesicles from obese individuals. Molecules with names like lysophosphatidylate and Then they did something clever. They exposed these vesicles to amyloid beta peptides, the proteins that form the sticky plaques found in the brains of Alzheimer's patients. The vesicles from obese tissue made the proteins clump together faster. The lipids they carried accelerated the aggregation process, the very process that is believed to drive neurodegeneration. This is not correlation. This is mechanism. The researchers demonstrated that fat tissue can send signals directly into the brain, and those signals can alter how quickly the hallmark pathology of Alzheimer's forms. Obesity has been known as a risk factor for Alzheimer's for years, yet the link was always murky, indirect, mediated through things like inflammation or insulin resistance. This research establishes a clear connection. Adipose tissue dispatches vesicles into circulation. These vesicles penetrate the blood-brain barrier. Within these vesicles are lipids that stimulate plaque development. A biological pathway exists, forming a circuit that links the body's fat reserves to the brain's most catastrophic condition. Nearly simultaneously, another research group at Purdue University released complementary discoveries. Their investigation focused on brain cells known as microglia, the immune sentinels tasked with defending neurons. In unaffected brains, microglia maintain constant surveillance, removing cellular waste, combating pathogens, and preserving equilibrium. However, in Alzheimer's affected brains, the microglia nearest to amyloid plaques exhibited distinct characteristics. They appeared enlarged, packed with lipid droplets, with fat building up within the cells themselves. The scientists, under the leadership of Professor Gareth Chopra, discovered that these lipid-laden microglia had lost their functional capacity. They became unable to eliminate plaques. They could no longer safeguard neurons. They were effectively immobilized by their excessive lipid load. The research team mapped out the biochemical mechanism. Upon encountering plaques and inflammatory signals, microglia begin generating free fatty acids. Under normal conditions, they would utilize these as energy sources. However, during the disease process, a malfunction occurs. An enzyme designated DGAT2 transforms the free fatty acids into triglycerol, representing fat in its storage form. This conversion happens at such excessive rates that the microglia become overwhelmed. Lipid droplets accumulate progressively. The cells lose their mobility. Their functions cease. Chopra characterized these accumulations as lipid plaques. This terminology mirrors the amyloid plaques that receive widespread attention, yet signifies a distinct problem, a concurrent pathology that has escaped notice for more than a century. Here lies the unexpected turn. The scientists evaluated two compounds, one that inhibits DGAT2 and another that accelerates its breakdown. The degradation method proved successful. It diminished the fat accumulation. It reinstated the microglia's capacity to consume amyloid plaques. It enhanced indicators of neuronal wellness in Alzheimer's animal models. This points toward a novel therapeutic approach, one that doesn't target the amyloid directly, but instead it reveals an avenue that pharmaceutical corporations have been overlooking, an avenue that bridges Alzheimer's investigation to lipid science, to metabolic disorders, to the 40% of America's population dealing with obesity. Consider the ramifications. Alzheimer's has undergone decades of examination as a disorder of protein misfolding, of amyloid and tau tangles, of plaques and neurological inflammation. Countless medications have been engineered to eliminate plaques or halt their genesis. The majority have proven unsuccessful. What if their failure stems from addressing the manifestation rather than the root cause? What if the genuine catalyst has been concealed in obvious view? Within the fat that saturates our cells and transmits signals we never recognized were being dispatched. The kingdom that prepared the world prior to the existence of forests, prior to the emergence of grass, prior to the first moss adhering to a moist stone at the ocean's periphery. Something else had already established its presence, not passively waiting, but actively working, decomposing stone, cycling nutritional elements, constructing the chemical infrastructure that would enable all subsequent life. We conceptualize terrestrial life as originating with plants, verdant pioneers establishing themselves on a barren terrain. However, the terrain was not barren upon plants' arrival. It had undergone preparation for hundreds of millions of years by a kingdom we scarcely acknowledge, fungi. On October 1st, 2025, scientists from the Okinawa Institute of Science and Technology released a manuscript in Nature, Ecology, and Evolution that fundamentally revises the chronology of terrestrial life, employing a synthesis of fossil documentation and an innovative method involving horizontal gene transfers, genetic material that migrates laterally between species instead of descending from parent to offspring. They traced fungi's origins to a period far more ancient than previous estimates suggested. The ancestral origin of all contemporary fungi existed sometime between 1.4 billion and 900 million years in the past. For context, terrestrial plants emerged approximately 470 million years ago. Fungi had been diversifying for potentially a billion years before any plant established roots. This represents more than a minor adjustment. This transforms the complete narrative. Complex, multicellular organisms, life forms composed of numerous cells with specialized functions, evolved independently precisely 5 times on Earth. Animals, terrestrial plants, fungi, red algae, and brown algae. Each category developed its own systems for cellular adhesion, intercommunication, and tissue organization. For most of these categories, fossil records establish definitive timestamps. Animals manifest around 600 million years ago in geological formations like the Ediacaran with their characteristic imprints. Red algae emerged possibly as early as 1.6 billion years ago in ancient seaweed, like fossils from India. However, fungi produce virtually no fossil evidence. Their structures are delicate, filamentous, rapidly decomposing. Determining their evolutionary timeline has been an enigma with absent components. The scientific team, directed by researcher Gergely Solisi, employed horizontal gene transfers as chronological markers. When genetic material from one fungal lineage transfers into another, it creates a constraint. The progenitor of the donor lineage must predate the descendant of the recipient lineage. Through identifying 17 such transfers and integrating them with the limited fossil documentation, the team established the fungal chronology with extraordinary accuracy. What materialized was an image of a kingdom that controlled Earth's landmasses for an almost unfathomable duration. Contemplate the significance. For hundreds of millions of years, potentially approaching a billion, fungi represented the most sophisticated life on terrestrial surfaces. They existed in isolation. Algae inhabited the oceans and presumably shallow coastal zones. Bacteria constituted microbial carpets. Yet fungi were distinctive. They performed chemical processes that no other organisms could execute. They release enzymes that dissolve rock, extracting phosphorus and additional nutrients imprisoned in minerals. They establish networks, mycelial filaments, that link distant soil regions, transporting resources across terrains. They forge partnerships with other organisms, trading nutrients for sugars, generating symbioses that advantage both participants. The scientists discovered evidence that certain early fungi possessed enzymes capable of decomposing pectin, a constituent of plant cell walls, dating back 1.2 billion to 800 million years ago. This indicates they were engaging with algae, potentially assisting their survival in the severe transition zone between aquatic and terrestrial environments. By the time plants ultimately evolved and commenced their colonization of continents, they encountered not a blank canvas. They discovered a world shaped by fungal operations, a world with rudimentary soils, with nutrient cycles already in place, with chemical processes already functioning. This inverts the pioneer mythology. Plants did not subjugate land independently. They inherited a world fungi had been modifying for ages. When plants did emerge, they established alliances with fungi almost instantaneously. We designate these alliances mycorrhizae. They are ubiquitous. 90% of terrestrial plants currently possess fungal collaborators dwelling in or surrounding their root systems, exchanging sugars for minerals. It is feasible, even probable, that plants could not have colonized land absent these alliances. Those alliances may have foundations, both physical and evolutionary, extending back to when fungi initially began engaging with algae in the primordial shallows, the vinegar that fooled the world. In March of 2024, a modest clinical investigation was released in a publication titled BMJ Nutrition, Prevention, and Health. The research originated from Lebanon, executed by scientists at Holy Spirit University of Koslik. It encompassed 120 young individuals, average age 17, all categorized as overweight or obese. The subjects were separated into 4 cohorts. 3 cohorts consumed apple cider vinegar each morning in quantities of 5, 10, or 15 milliliters, combined with water, and administered before meals. The fourth cohort received a placebo, counterfeit vinegar that appeared and tasted comparable but lacked the active component, acetic acid. The investigation spanned 12 weeks. The outcomes, according to the released manuscript, were extraordinary. The vinegar consumers experienced weight reduction, not insignificantly, 6 to 8 kilograms on average, with those consuming the maximum quantity observing the greatest decreases. Their body mass index declined, their waist and hip measurements contracted, their blood glucose, triglycerides, and cholesterol all demonstrated improvement. The manuscript proposed that apple cider vinegar decelerated gastric emptying, enhancing satiety sensations and diminishing appetite. It displayed graphs and statistical evaluations demonstrating clear, significant distinctions between the vinegar cohorts and the placebo cohort. The publication released the research with a press announcement. Media organizations globally featured it. Headlines declared a straightforward, inexpensive remedy to obesity. Apple cider vinegar, a standard pantry commodity, suddenly framed as a weight reduction phenomenon. The research achieved viral status. Articles proliferated. Social media personalities commenced advocating daily vinegar consumption. The apple cider vinegar industry, already assessed at exceeding $1 billion, experienced renewed attention. Individuals referenced the research in discussion forums, in web articles, in dialogues with acquaintances. It possessed the credibility of peer-reviewed science supporting it. Released in a publication associated with the BMJ Group, a distinguished name in medical publishing. However, certain scientists maintained skepticism from the beginning. An individual named James Heathers, a research integrity specialist, initiated examination of the manuscript shortly following its appearance. His discoveries troubled him. The age and body mass index distributions among the 4 cohorts were virtually identical. Statistically, this is improbable. When randomly allocating individuals to cohorts, variation is anticipated. Yet, the cohorts in this research appeared excessively similar, as though they had been perfectly equilibrated rather than randomly assigned. Heathers released an evaluation in May of 2024, describing what he characterized as implausible configurations in the data. He indicated that if the outcomes were authentic, apple cider vinegar would demonstrate 50% greater effectiveness than medications like Ozempic, pharmaceuticals that require thousands of dollars, and medical prescriptions. A tablespoon of vinegar achieving superior outcomes than advanced pharmaceutical interventions challenged plausibility. Additional scientists expressed concerns through correspondence to the publication. The research had not been pre-registered, a mandate under BMJ Group editorial standards designed to prevent selective outcome reporting. The statistical approaches were ambiguous. Efforts to duplicate the evaluations from the released data proved unsuccessful. The BMJ Group's Content Integrity Division initiated an inquiry. They submitted the manuscript to independent statisticians, requesting evaluation of its dependability and attempts to reconstruct the discoveries. The statisticians were unsuccessful. They detected multiple analytical mistakes. They identified anomalies in the dataset that indicated the fundamental data required independent examination. The unprocessed figures were inconsistent. On September 23, 2025, 18 months following the initial release, the publication retracted the manuscript. The retraction statement was direct. The outcomes were undependable. multiple mistakes had been detected. The data could not be authenticated. The authors, in their statement, characterized the mistakes as unintentional errors and concurred with the retraction determination. However, the harm had been inflicted. For a year and a half, the research had been referenced as proof. It featured in systematic assessments, meta-analyses that compile outcomes from multiple investigations to formulate broader determinations. One such assessment, released shortly preceding the retraction, depended partially on the invalid data to propose that apple cider vinegar might assist with weight regulation. That assessment is now undermined, constructed on a foundation that incorporates fabricated or profoundly defective outcomes. An editor at BMJ Group, a woman named Helen MacDonald, issued a public declaration, appealing though it is to inform readers of an apparently straightforward and seemingly beneficial weight reduction aid. She stated, "Currently, the outcomes of the research are undependable, and journalists and others should no longer cite or utilize the outcomes of this research in any subsequent reporting." Yet how many articles persist online, uncorrected, still referencing the retracted investigation? How many individuals modified their conduct based on information that proved to be fallacious? The moon's divided heart. Our moon possesses two faces, and they are not equivalent. Anyone with astronomical viewing equipment can observe this. The near side, the surface that perpetually faces toward Earth, is marked with dark regions designated Maria, ancient lava plains that occupied impact basins billions of years previously. The far side, concealed from our observation until spacecraft orbit behind it, appears entirely dissimilar. Fewer Maria, more craters, a terrain that seems more ancient, less modified by volcanic processes. For decades, this asymmetry has perplexed planetary scientists. Why would one hemisphere of the moon differ so dramatically from the other? They constitute components of the identical body, formed from identical material, shaped by identical cosmic history. Or so our assumption was. On October 3, 2025, scientists released an examination of lunar specimens obtained from the far side by China's Change 6 expedition. These represent the first specimens ever retrieved from that hemisphere, and they convey a narrative that challenges what we accepted about the moon's interior. The rocks are abundant in minerals that develop from magma, molten rock that cooled and solidified. However, the chemistry is anomalous. The specimens contain fewer heat-generating elements, fewer radioactive isotopes of potassium, thorium, and uranium than rocks from the near side. This is meaningful because those elements are what maintain a planetary interior's temperature. They decay across billions of years, releasing energy that can stimulate volcanic processes, that can liquefy rock and propel it flowing to the surface. The scientists determined that the far side developed from cooler magma, not marginally cooler, considerably cooler. This indicates that the moon's interior is not homogeneous. It is not a straightforward layered sphere with a crust, mantle, and core arranged symmetrically. Asymmetry is integrated into its profound structure. The distinction in composition and temperature between the near side and far side that originates from the moon's formation. The prevailing hypothesis for how the moon formed early in Earth's history, approximately 4.5 billion years previously, a Mars-sized object collided with our planet. The impact was so catastrophic it vaporized rock, generating a disk of debris in orbit around Earth. That debris coalesced, drawn together by gravity, constituting the Moon. However, the process was not uniform or orderly. The Moon was presumably molten initially, a sphere of magma cooling gradually across millions of years. As it cooled, denser minerals descended. Lighter minerals ascended, establishing layers. The recent discoveries indicate this process transpired differently on the two hemispheres. Perhaps the near side facing Earth absorbed more thermal energy from tidal forces, from the gravitational influence of our substantially larger planet flexing and warming the interior. Perhaps the distribution of radioactive elements was uneven from inception, concentrated more substantially on one side. Whatever the explanation, the consequence is a moon with a divided core. This matters beyond merely lunar geology. It informs us about how rocky bodies develop and transform. We tend to presume symmetry, to model planets and moons as spheres with uniform layers. However, if the moon, which is relatively small and uncomplicated compared to a planet, can possess such fundamental internal asymmetry, what does that signify for other worlds? Mars possesses hemispheres that appear drastically different. The northern lowlands, smooth and level. The southern highlands, ancient and cratered. Could Mars also possess an asymmetric interior with distinct thermal histories on each side? What about exoplanets? The thousands of worlds we've identified orbiting other stars. We cannot observe their interiors. However, if asymmetry is widespread, our models might be fundamentally incorrect. The specimens also disclosed something additional. They verified the volcanic activity on the far side terminated earlier than on the near side. With fewer heat-generating elements, the far side could not maintain volcanism as prolonged. It became dormant while the near side was still erupting, still occupying basins with lava. This generates a type of geological documentation, a chronology inscribed in rock, demonstrating how the moon's thermal budget diminished across billions of years. By examining these specimens, scientists can constrain models of planetary cooling, of how prolonged it requires for a world to freeze internally, to become geologically inactive. The ice that hides an ocean. Saturn possesses dozens of moons, yet one of them continues attracting scientists back, continues generating headlines, continues suggesting that we might not exist alone, even in our own solar system. Enceladus, a small world merely approximately 500 kilometers across, enveloped in ice so luminous it reflects virtually all the sunlight that contacts it. From a distance, it appears pristine, frozen, lifeless. However, in 2005, the Cassini spacecraft approached close enough to observe what was actually occurring. Enceladus is not lifeless. It is erupting. From fractures near its south pole, massive plumes of water vapor and ice particles propel into space. Geysers that ascend hundreds of kilometers above the surface. These are not sporadic occurrences. They're continuous, constant, supplied by something beneath the ice, an ocean. A global ocean of liquid water, tens of kilometers deep, situated beneath a shell of ice, perhaps 20 to 30 kilometers thick. The ocean is maintained liquid by tidal heating, the identical type of gravitational flexing that maintains Jupiter's moon, Io, volcanically active. Saturn's gravity compresses and extends Enceladus as it orbits, producing friction in the moon's interior, generating heat, melting ice that should, by all expectations, be frozen solid. Cassini traversed through the plumes. It sampled them, examined their chemistry with onboard instruments. The discoveries were exceptional. Water, obviously, but also salts. Evidence of rock-water interactions occurring on the ocean floor. Silica particles, minute grains of silicon dioxide that develop when heated water interacts with rock at temperatures exceeding 90 degrees. And organic molecules, elementary ones initially, methane, carbon dioxide, compounds containing carbon but not necessarily signifying life. Then, in subsequent flybys, more sophisticated molecules, propane, ethane, acetylene, and now, according to recent examination of Cassini data, released on October 2nd, 2025, even more sophisticated organics imprisoned inside the ice grains. The scientists re-examined data that Cassini gathered years previously, implementing new methodologies and models to retrieve information that was not apparent in the initial investigations. What they discovered were organic compounds with multiple carbon atoms, molecules that on Earth are connected with biological processes, though they can also develop through non-biological chemistry. The existence of these compounds does not establish life, yet it reinforces the argument that the conditions inside Enceladus Ocean could sustain life. Liquid water, energy from tidal heating, organic molecules, rocky surfaces where chemistry can transpire. These are the components we seek when we search for habitable environments. Here is what renders Enceladus so compelling. The ocean is not isolated. It is connected directly to space through those plumes. Anything dissolved in the ocean water, any molecules, any cells, if they exist, can be transported up through the fractures and expelled into space. This signifies we do not need to land on Enceladus, penetrate through kilometers of ice, and lower instruments into a dark ocean. We simply need to traverse through the plumes and gather specimens. In principle, we could identify life without ever contacting the surface. NASA and other space agencies have been deliberating missions to execute precisely this. Spacecraft engineered to orbit Saturn make repeated passages through the plumes and examine the material with instruments far more sensitive than what Cassini transported. However, there is a frustration here. Similar to the Mars Sample Return Challenge, these missions are proposed, investigated, engineered, and then postponed. Budget limitations, competing priorities, technical obstacles, political transitions. The earliest any dedicated Enceladus mission might launch is the mid to late 2030s. That is a decade or more distant. Meanwhile, the evidence accumulates. Every new examination of Cassini data discloses more complexity, more indications that Enceladus is not merely habitable, but might actually be inhabited. We possess a world with an ocean, with energy, with organic chemistry expelling its secrets directly into space for us to sample, and we are waiting. Saturn possesses other moons with subsurface oceans. Titan, the giant, with its dense atmosphere and methane lakes, almost certainly possesses a water ocean deep beneath its icy shell. Jupiter's moon Europa possesses an ocean that might contain twice as much water as all of Earth's oceans combined. Ganymede and Callisto, presumably, possess oceans as well. Our solar system, it appears, is not arid. It is aqueous, filled with concealed seas, secured beneath ice. oceans that have existed there for billions of years, stable, protected from radiation, possibly flourishing with life we have not yet conceived. The hunter before blood. When you contemplate a leech, you presumably envision something disagreeable, a dark, slug-like organism attaching to skin, consuming blood, leaving a wound that bleeds longer than it should because of anticoagulants in the leech's saliva. Leeches are parasites, organisms that survive by extracting from others. They are soft-bodied, difficult to appreciate, and generally absent from the fossil documentation because soft tissue seldom preserves. However, on October 2nd, 2025, scientists announced the identification of a leech fossil that transforms everything we presumed we understood about these organisms. It is 430 million years old, advancing the origin of leeches back 200 million years earlier than any previous evidence. The fossil originates from a formation that preserves exceptional detail, capturing not merely the outline of the animal, but the structure of its body segments, the configuration of its head, even suggestions of its internal anatomy. What astonishes paleontologists is not merely the age. It is what the fossil discloses about what leeches were before they became parasites. This ancient leech was not a blood consumer. It was a hunter, an active predator with jaws and a body constructed for movement in open water. It inhabited the ocean, not in freshwater ponds or terrestrial environments where modern leeches are discovered. It was, in every sense, a different category of animal from the leeches we recognize today. Modern leeches belong to a classification designated Hirodinia within the larger Annelida, the segmented worms. They're closely related to earthworms and marine bristleworms, all sharing a body plan constructed from repeating segments. However, leeches lost the bristles, lost the rigid cheetah that other annelids utilize for traction. Instead, they evolved suckers, one at each end of the body, and a muscular, flexible form that allows them to inch along surfaces or swim with undulating waves. Most significantly, many leeches evolved specialized mouth structures for piercing skin and consuming blood, a lifestyle that requires biochemical adaptations, enzymes to prevent clotting, and anesthetics to avoid detection, all packaged into saliva that transforms a simple bite into a sophisticated parasitic strategy. However, 430 million years ago, none of that had occurred yet. The fossil leech possessed a different body, longer, more streamlined, constructed for speed rather than attachment. Its jaws were sharp, but not adapted for piercing skin. They were for grasping, for securing prey, for dismembering small invertebrates in the water column. This was a carnivore, an ocean predator that swam actively and hunted other animals. The scientists who examined the fossil, releasing their discoveries in a peer-reviewed publication, characterized it as a portal into a vanished world, a time when leeches were not the parasites we despise, but were legitimate hunters in marine ecosystems. This identification necessitates a reconceptualization of leech evolution. The parasitic lifestyle, the blood-feeding behavior, emerged later. It was not the ancestral condition. Somewhere in the subsequent millions of years, some lineage of hunting leeches altered strategies. Perhaps they commenced scavenging on deceased animals, feeding on wounds. Perhaps they transitioned to feeding on living animals opportunistically, consuming small amounts of blood when the opportunity presented itself. Across time, those opportunistic feeders became specialists, perfecting their mouth structures, their saliva, their behavior, until they became the obligate parasites we observe today. However, the fossil demonstrates that leeches, it raises a question. Are there still hunting leeches existing? Undiscovered lineages that never made the transition to parasitism. The ocean is vast and inadequately explored. We possess superior maps of the surface of Mars than of the deep sea floor. New species are identified constantly. Strange worms and bizarre invertebrates that do not conform to existing classifications. It is entirely feasible that somewhere in the deep ocean, in a trench or canyon we have never visited, there are leeches that still hunt, that still exist the way their ancestors did 430 million years ago. The fossil is a reminder that evolution is not a linear progression, not a march toward complexity or improvement. It is a branching tree with lineages diverging, experimenting, some succeeding, and some becoming extinct, each adapting to the environment and opportunities available. How words rewrite reality. There exists a form of manipulation so subtle, so insidious, that the victim does not recognize it is occurring until their grasp on reality is already weakened. It possesses a name: gaslighting. The term originates from a 1938 play, subsequently a film, in which a husband systematically manipulates his wife into questioning her own perceptions, her own memory, her own sanity. He dims the gaslights in their residence, and then insists they have not changed. He conceals objects and claims she misplaced them. He contradicts her recollections until she no longer trusts herself. The play was fiction, but the phenomenon it portrayed is devastatingly authentic. On October 2nd, 2025, scientists at McGill University and the University of Toronto released discoveries that reconceptualize gaslighting not as simple deception, but as a learning process rooted in how our brains process conflicting information. The investigation, released in a peer-reviewed neuroscience publication, characterizes gaslighting as a form of associative learning gone awry, where repeated exposure to false information from a trusted source can override direct sensory experience. Your brain, they clarify, is constantly attempting to construct a model of the world, a mental representation that predicts what will occur next. This model is updated based on two streams of information: what you perceive directly through your senses, and what you learn from others, especially people you trust. Under normal circumstances, these two streams complement each other. You observe a red apple. Someone tells you it is a red apple. The information corresponds, and your model is reinforced. However, gaslighting generates a conflict. You observe a red apple. Someone you trust tells you it is green. Now your brain encounters a problem. It must determine which source of information to weight more heavily. If the person contradicting you is someone you depend on, someone who has been reliable in the past, someone with social or emotional power over you, your brain may choose to trust them over your own eyes, not consciously, not as a deliberate decision, but as an automatic adjustment in the learning algorithm your brain utilizes to navigate the world. The scientists employed brain imaging and behavioral experiments to investigate this process. They presented participants a series of images and then had confederates, people collaborating with the experimenters, provide false information about what the images contained. The confederates were presented as experts, as people with specialized knowledge, establishing a context where their statements carried authority. Over repeated trials, the participants commenced doubting their own perceptions. When asked to recall what they had observed, they increasingly reported the false information provided by the Confederates rather than what they had actually witnessed. The brain scans demonstrated activity in regions associated with conflict resolution and memory reconsolidation, areas that activate when the brain is rewriting stored information to incorporate new data. This is not stupidity. This is not weakness. This is the brain executing what it evolved to do, which is to learn from others. Humans are social animals. We survive by sharing information, by trusting the knowledge of our community. If everyone in your group tells you that a certain plant is poisonous, you do not need to consume it yourself to discover. You trust them, and that trust maintains you alive. However, this same mechanism, this social learning system, can be weaponized. If someone with power over you consistently contradicts your experience, your brain may begin to prioritize their version of events over your own memory. You start to doubt yourself. You question your perceptions. You feel confused, disoriented, as if you're losing your grasp on reality. In a sense, you are. Your internal model of the world is being rewritten by someone else's words. The implications are profound. Gaslighting is not merely psychological abuse in the abstract sense. It is a direct manipulation of neural processes, an exploitation of how the brain learns and remembers. The scientists emphasize that understanding this mechanism is the first step toward defending against it. If you know that your brain is vulnerable to authoritative contradictions, you can construct safeguards. You can maintain records, write things down, take photographs, create external anchors for your memory that cannot be erased by someone else's insistence. You can seek validation from multiple sources, checking your perceptions against people outside the manipulative relationship.